Coordinating entities in a distributed system has been a long-standing problem in computing. Without a central coordinator calling the shots, how do you find a way to get everyone on the same page? This is the Byzantine generals problem, in which, in order to avoid catastrophic failure of a system, the system's actors must communicate with each other and agree on a single truth. But some of these actors may be unreliable. This dilemma is very applicable in computer science. Systems that can overcome the problem are said to be Byzantine fault tolerant. In blockchains, the Byzantine generals problem is mitigated by allowing all users on the network to validate the information. In the interest of precision, we'll stop referring to users as users and call them nodes instead. In the decentralized environment we're trying to create, nodes don't, or at least shouldn't, trust their peers, unknowingly passing you false information. To combat the spread of false information, we use a blockchain to sequence the messages as they appear. If nodes want to submit a message, which in our case is a block, then they need to put in some work to prove that they're serious. This is the logic behind proof of work, a type of consensus mechanism allowing nodes to coordinate in a distributed setting. Such mechanisms ensure that all agents in the system can agree on a single truth, even if some agents fail. In proof of work, hashing is used, as we've discussed before. What we didn't mention is that there's a specific hash that nodes need to find. They hash the contents of the block they want to broadcast to the network and hope the hash matches the parameters set out by the blockchain. Remember that our block must also include the hash of the previous block, so it can only be created after the most recent one. In proof of work systems, it's often incredibly difficult to calculate a valid hash. Nodes use large amounts of computational power and electricity to do this. But here's the thing. Once they do find one, they send the block around the network. Anyone can easily check that it's valid and hasn't been edited, because they only need to hash it once to see whether it produces a correct hash. They'll check all of the information inside the block too, whether it was built on a previous block and whether the transactions are authentic. This dynamic, expensive to produce, cheap to verify, is some of the game theory that makes blockchain systems viable. You'll be out of pocket if you produce an invalid block, as the other nodes will immediately reject it. Proof of work was the first consensus mechanism to surface and remains important. This process of using proof of work to solve a block is called mining, and nodes that participate in mining are called miners. We call them miners because they're working to extract a reward from the protocol. Despite proof of work's strength for preventing system abuses with a high level of security, it has some limitations. For one thing, when the network becomes larger, it requires expensive equipment and high energy usage. Therefore, alternative consensus mechanisms were introduced to mitigate these limitations. A prominent alternative consensus mechanism is called proof of stake, which was proposed back in 2011. Proof of stake mechanisms use a pseudo-random election process to select validators from a group of nodes. The validators hold and stake the native cryptocurrency of the blockchain in order to validate transactions. Staking refers to the act of validators committing funds to the blockchain network. The locked funds will then act as collateral, meaning malicious validators will most likely lose their stake and be kicked out. On the other hand, honest validators will be rewarded as new blocks are produced. Generally, the more coins are staked, the more likely you get to validate a new block and receive rewards. Beside proof of work and proof of stake, there are other alternative consensus mechanisms. Delegated proof of stake and hybrid PoW PoS are two examples. To sum up, consensus mechanisms are critical to allow distributed systems to work together and stay secure, and proof of work and proof of stake are two dominant mechanisms.